Ms. Sheppel, do you have like another thing in notes?
No, not for you. Should have been here on time.
We had to clean up a lab. You should get an email, I think.
All right. So the next thing we're talking about is really just going to use all the stuff that we have been doing. So it's not going away. It'll give you more practice with that and kind of help you along the way there. We will spend probably all week on this section. That's a rough plan, so we'll probably do maybe a quiz Friday over just this section before we move on. So talking about a definite integral. So we've been seeing these limit problems. That's like the last one we had on our quiz, where we are doing a limit as n approached infinity, and we had to use our summation rules to try to calculate that. And we have those come up when we were finding areas. Another situation we might see that is if we are talking about distance. It actually happens in a lot of different scenarios. Not everything has to be positive. You know, area and distance are positive things, but this limit isn't limited to those. So we are going to use a definite integral, and it's just another, maybe more concise way of writing this ugly thing that we've been seeing show up. So the limit and the sum, these two things together are going to turn into an integral, which is like a tall, skinny S looking thing. And we are going to have a starting and a stopping point from A to B. So that would be normally, I would tell you find the area from 0 to 4 or from 1 to 7. Okay, your lower number goes on the bottom, your upper number goes on top. This f of x sub I, remember when we were doing them, we had to find our change in x and our x sub I. So this is just the function. And that change in x that we've been multiplying by gets replaced with a dx symbol. So we're basically taking out the funny looking I and just writing f of x. We're taking out the limit and the sum, we're replacing it with this integral symbol. All right, we are going to talk a lot about this and its applications. Today we're going to basically take those problems that we were doing and use that integral to solve them. Just some notation things. F of x is the thing we are integrating, so it's called the integrand. A and B are the limits of integration. A is the lower limit, our starting point, and B is the upper limit. The other thing I want to stress, anytime you have this integral symbol, you have to have the dx with it. Okay, so you can't have one without the other, they go together. D of x is really just telling us what our variable is, so just get used to writing those things at the same time. So this is the type of problem that we were solving, and we're going to talk about how to use our integral to actually do this. So we know that we talked about originally doing rectangles, and we could do over and under estimates, and the more rectangles we have, the better it is. So to get the true area, we had to let the limit go to infinity, right? The number of rectangles had to be approaching infinity. We do also have to consider, we haven't seen this, but if things were below the axis, that would be negatives. Above the axis would be positive. So would it be possible to have a negative area in this respect? Sure, if something had more below the axis. So that's something that has not shown up in our problems yet, because we only had functions that were strictly above the x-axis, but we will now have some that are below. So that's considered to be your net area, the positive area minus the negative area. All right. So our theorem is just telling us if you have a continuous function, then we can find the integral, or we can integrate it. If it has some jumps, as long as it's a set number of jumps, we could calculate each of those little areas. So as long as our function is continuous, we can do the problem. And when we're setting it up, it's just taking the place of that calculation we've already been doing. We know the change in x was your ending minus your beginning divided by n. Your x sub I was your starting point plus the change in x times I. That's what we were doing on all of those problems. So I want to use what we know to find this integral. Okay, so the way we've been doing them, like the last question on our quiz, we had to find the change in x. Your ending minus your beginning over n. So we're ending at 4, starting at 0. So my change in x is 4 over n. X sub I is your starting point. Where does this one start? 0 plus the change in x times I, which is 4 over n. Okay. So this integral, that's representing the limit as n goes to infinity of the sum from 1 to n. My function, what am I replacing my x's with?
X plus 3 minus 2x.
Well, that's the function I'm plugging into. So I'm going to replace, for each of those x's, we're going to plug in.
Oh, 4 over ni.
And dx just means the change in x, which was 4 over n. So that's length times width. All right, so this is what we were doing before. So we know we need to multiply this out and simplify it as much as possible. All right, so 4 cubed is 64. Can I distribute this 4 over n at the same time? So that would give me 256 over n to the 4th I cubed minus 32 over n squared I. And then what did we do? Yeah. So the I cubed formula is n squared times n plus 1 squared over minus 32 over n squared. The I formula is n times n plus 1 over 2. So lots of algebra here. N squared, so I can cancel 2 of these. 256 divided by 4 is 64. I'll cancel one of those ends. This will be 16. Can I distribute and FOIL this at once? So n plus 1 squared, that's n squared plus 2n plus 1. So I get 64n squared over n squared. So that's 64. Plus 128n over n squared, so 128 over n. So 64 over n squared. I need to distribute a negative 16 over n. So 16 n over n would be 16 and 16 over n. And then if n is going to infinity, a number over infinity goes to 0. So we get 64 plus 0 plus 0 minus 16 minus 0. So 48.
So how is this different than what we were doing?
It's not. It's written in a different notation. So
So
all I
it's the
want you to
same
see
thing.
is, yep, this notation is just a different way of doing the same thing. Corbett, pick your head up. Why?
I don't know.
Okay. Want to try another one? You can come in if you want. I'm going to, let's go to this one. Okay, so I'm not asking you to calculate anything on this one. I'm just asking you to write this with an integral. Okay, so we know the limit and the sum, those turn into an integral. What are my starting and stopping points? Starting from -3 to +2. And it is important that the starting one goes on the bottom and the ending one goes on top. You with me, Corbin? Okay. So in here, we have a 2 minus 3. When you see x sub I, what is that going to get changed to?
Change in, no, something.
Just-
plus
just
the negative 3.
And you just put an x with it. So basically, the integral didn't have i's with it. So we're just going back and forth between the two notations. And the change in x, what did I say we are going to replace that with? Dx. Look back at that very first thing we had today, right here. I told you the limit and the sum were the integrals. F of x sub I is just our function with an x for our variable. And the change in x is just the dx. So we just have to be able to use either notation.
Wait, so why are we not doing the little negative 3 over, or negative 3 plus 2 over n?
Because I didn't ask you to calculate it, I just asked you to write it as an integral.
So you don't calculate it when you write it in this?
Well, I could ask you to calculate it, but my question, I just wanted to see if you could go back and forth between the notations.
Yeah, but isn't that what this, I'm just confused, like why is that not what this is? I thought this right here was this. Is that not?
It is, but we're just not working out the whole problem. Like if I told you to then work that, we'd have to do all of this. Okay, I'm just trying to get you to use both notations.
So this is just x, and this is dx, every time.
Every time.
Okay.
Alright. So if I asked you to actually evaluate the integral, so this is kind of like the last one we just worked out together. So this one I'm not asking just for a notation, I ask you to evaluate it. So what is my change in x?
3 over n.
Right, because you have to do 5 minus 2 over n. Alright, your x sub I is what?
2 plus 3 over n I.
Good. Alright, so if I actually want to work it out, we're doing the limit as n goes to infinity of the sum from 1 to n. My function, you are going to that and you're replacing your x's with this 2 plus 3 over n I. And dx, what am I changing that to? Alright. So now we have a lot of algebra to do. So we have to square, distribute the 3, and also distribute that 3 over n. Okay? So think about FOILing. So that would be a 4 times 3 is 12 times 3 over n, so 36 over n. This would be plus 12 over n times 3 is 36 over n times 3 over n, so 108 over n squared. Then this would be 9 over n squared I squared times 3 would be 27 times 3 over n would be 4 times 3 over n is 12. And you might need to write more out than I did there. And you're welcome to. So what I did. So if I squared this. And I distributed my 3. And then I distributed my 3 over n. So that's kind of my work for how I got there. Is everybody with me? Okay. So now we can do summation. 36 over n. It doesn't have an I with it, so it's a constant. When you add up constants, what do you have to do? Mm-hmm. So this is 36 over n times n. Okay, this is 108 over n squared. Formula for I is n plus 1 over 2. 1 over n cubed. Formula for I squared. And 12 over n also doesn't have an I with it, so it's a constant. Notice once I do my formulas, then that I goes away. Or sorry, my summation goes away once I do my formulas. All right. So, let's see. This would be 36. 108 divided by 2 is 54. So you get 54 n over n. Plus 54 over n. So 54 n squared over 2 n squared. 81 n over 2 n squared. 27 over 2 n squared. So if n goes to infinity, anything with an n on the bottom would turn into 0. 120. So it's the integral from where to where?
0 to pi.
In my function, all of these xi's just change to an x. So it would be x to the plus, and change in x gets replaced with dx, and that's it. Okay? So I'm going to give you this handout. It is actually the homework for today and tomorrow. You're able to do part of it now, but I want to go over a couple things. So, 1 through 5 are just like this example, writing the integrals. So they should be pretty short. One thing I want to talk about, like problem number 3, you'll notice it has a sum. Instead of x sub I, it has m sub I. But it still has change in x. The fact that it says change in x tells me my variable is x. Tomorrow we're going to talk about m being a midpoint. But for the term, in terms of writing the integral, that m sub I is going to get changed to an x, just like anything else. Okay, so it's just like an x sub I. So when you write your integral, this would be the integral from where to where?
4 to 9.
And my function would be square root of x, and change in x would be dx. And that's all you're doing in problem 3. Okay? So that's 1 through 5. 6 through 9, we are going to talk more about that tomorrow. So why don't you skip those. 10 through 14, you are able to do now. We've done a couple of those today. It's like the old stuff. You might need more space, so you might need to do those on another sheet of paper. But tomorrow I'll talk about the midpoint sum, and you will have some time